Okay, so as we said, with boiling point, many physical properties are dictated by intermolecular forces. Okay, of course, when we want to go from the liquid phase to the gas phase, there's a big difference between the interactions between the water molecules. When water is in liquid phase, they have a lot of interaction. When they go to the gas phase, which is what comprises bubbles within a boiling liquid, the molecule in the gas phase, you have to overcome or break that hydrogen bonding to make sure that the water molecules are now in the gas phase. So the strength of the intermolecular forces are going to dictate the boiling point and, in fact, the melting point. So as your intermolecular forces increase, your boiling point goes up and your melting point goes up. It takes more energy to go from the solid phase to the liquid phase. Okay. Another intermolecular force another property that intermolecular forces dictate are, of course, solubility. We'll talk about solubility of ionic compounds in liquid phases in the next unit, but right now we're going to talk about liquids, so we're referring to miscibility. We know oil and water don't mix. You can think of this pentane molecule as your oil and water. They don't mix because the water has a very strong interaction, hydrogen bonding. Pentane only has dispersion forces, a very weak interaction. So to mix, the pentane molecule has to overcome the hydrogen bonding, and the water now has to have a stronger interaction with the pentane molecule. That is not the case, so pentane is not miscible in water. And in general, that sets up a rule of thumb that like dissolves like. So here we have in A, we have a water, polar on top because it's less dense. And then CH2Cl2, a nonpolar compound, on the bottom because it's more dense. When you add a nonpolar compound to this, the iodine, it stays and dissolves in the nonpolar solvent. If you add nickel nitrate, a polar compound, it will dissolve in the polar compound because the intermolecular forces are more compatible, like dissolves like. Okay. Analogous to boiling point, intermolecular forces also affect the rate of evaporation. I know if I spill water on a desk or on the floor, it's not going to be there forever. It's going to evaporate. Water is going to go into the gas phase without me certainly boiling it. Okay. Now, just the same is true though for evaporation and boiling point. These water molecules have to break the interaction, the hydrogen bonding between the other water molecules before they can go into the gas phase. Okay, the hydrogen bonding is what keeps them there. So if you supply them enough energy, if you boil them, they'll all leave. But it turns out that at even room temperature, some water molecules have enough kinetic energy to overcome the hydrogen bonding. Okay, and you can see that by the plot of a fraction of molecules as a function of kinetic energy, very similar to the plots of velocity for different gases that we looked at in the gases unit. Okay, we know that the kinetic energy of a sample, not all the molecules in that sample have the same kinetic energy. They have a Boltzmann distribution. So it turns out that just at room temperature, let's call lower temperature room temperature, a small percentage of molecules have enough energy, have enough kinetic energy to overcome the energy needed to break the intermolecular forces. If you increase the temperature, you shift the distribution to the right, and now a larger number of a higher percentage of molecules have enough energy. Okay, and that of course determines the differences between molecules. Ethanol evaporates much more quickly than water because ethanol has weaker intermolecular forces. So therefore, if we would draw this would be, say this is ethanol, this is water. So now if water at any temperature, a larger number of ethanol molecules have enough kinetic energy than water to evaporate. Okay. So a quantitative approach to talk about evaporation rates is actually referring to a substance's vapor pressure. Okay, and that is the pressure that the gas has in a closed container after it reaches equilibrium. Okay, so when you first put a liquid such as water in a container, it's going to start to evaporate. It's going to continue to evaporate, and the rate of evaporation is constant at constant temperature. But as the number of molecules in the gas phase increase, they are going to start to condense back into the liquid phase. And of course, at initial time, when you don't have any gas molecules, it's zero. So the rate of condensation increases as a function of time. When the two rates equal, which is the definition of equilibrium, rates of the forward or reverse reactions are equal. When they equal out, we can measure that pressure, and that is our vapor pressure. The pressure of the gases in a closed container after it's reached equilibrium. And when we refer to the boiling point of substance, what we're referring to is when the vapor pressure equals the atmospheric pressure. Okay, and so if you plot vapor pressure as a function of temperature, whenever the vapor pressure equals atmospheric pressure at whatever temperature that occurs, that is the boiling point of that liquid. 100 degrees Celsius for water, 78.3 degrees Celsius for ethanol, and then 34.6 degrees Celsius for diethyl ether. Okay, and we can predict which molecules have the stronger intermolecular forces by the boiling points. Water having the strongest, then ethanol, diethyl ether having a much weaker intermolecular force. So it takes a lower kinetic energy to overcome the intermolecular forces. Okay, intermolecular forces also contribute to the effect of surface tension. Everyone's seen probably a video or image of a insect walking on water, not becoming submerged. Here's an image of a paper clip floating over on water. Here's an image of a very large water droplet, and what keeping those water droplets together is, of course, surface tension. And so if you want to submerge something or break that, what you have to do is you have to break those intermolecular forces. And if you don't have enough force to do so, you're not going to break that surface tension. Surface tension also causes capillary action, or the flow of water through a very small inner diameter glass tube. That same effect is observed causing meniscus. Glass is made out of silicates, quartz. They have polar groups on them, so the water is attracted to the polar group in the glass. Mercury is a nonpolar compound, so it is not attracted to the intermolecular forces, and actually you can think of it as being repelled, so it tries to pile up in the middle to get away from the polar groups in the quartz, and so that's what we refer to as a reverse meniscus. The attraction for the polar groups in the glass actually causes water to overcome the forces of gravity, and so water will travel up sometimes, depending on the inner diameter of the capillary, sometimes great distances.